This tutorial is a continuation of modes of heat transfer. We've already looked at radiation, and today we're going to look at two others, conduction and convection. We're going to mathematically model conduction, and in convection we just want to understand from a conceptual standpoint, be able to compare and contrast that to conduction and radiation. Okay, so let's start with conduction, which is probably the most common, what people most associate with heat transfer. You touch something that's either hotter or colder than you, and you have heat flow in or out of you depending on the temperature difference. It's a fairly straightforward concept. We'll look at it microscopically as well, which is straightforward, but the math is a little bit difficult, or at least the modeling of it. Okay, so to help us out, we're going to look at a pictorial, if you will, schematic of heat flow via conduction. Okay, so that's just when two or more materials are in contact. And it's critical that the two materials are at different temperatures. And I think that goes without saying. Any heat flow has to happen because of temperature differences. So let's say we have a hot reservoir here. We have a cold reservoir here. They are in contact with one another with some material, okay, that is a cross-sectional area A, and it is L long. Okay, so we could shorten the distance between them, we can make it wider, we can make the reservoirs arbitrarily big. I've made it such that our area is smaller than the reservoir, and that reservoir maintains its temperature. We'll keep that simple. So if this hot temperature is, let's say, at 100 Celsius, and this is at 20 Celsius, we'll assume that those temperatures stay the same throughout the heat conduction process. We know from experience that they can certainly change and reach equilibrium, but that's not really the main issue here. Okay, so we can ask ourselves, what factors matter in the heat flow, which we will call H dot, okay? And H dot, by definition, is the rate at which heat is flowing out. So it's really dq dt. I'm just going to put it as Q over T. Okay, well, the most obvious thing that matters, and I'll write this down later, is the difference in temperature. The bigger the temperature difference, the faster heat's going to flow. Because that follows from if they're at the same temperature, there's going to be no heat flow. Maybe also what matters is we know material. We know that metals conduct heat a whole lot better than nonmetals. So we have a constant that reflects the conductivity of a metal, which will reflect in our equation. Less obvious are the two other parameters, and that is area and the length. Okay, I think we can work out that the more area in contact with one another, the more conduits, if you will, the more paths the particles have to change their kinetic energy from high to low or low to high. So we're going to see that it's proportional to area. And then maybe the least obvious is the effective length. But the further apart the reservoirs are, the slower the rate of heat transfer is going to be. So we see an inverse relationship with L. So putting it all together, we see that the heat flow rate is equal to K. K is the conductivity of the material. A, that's the area, the contact between the two reservoirs. And then delta T all over L. And sometimes that delta T over L is looked at as one unit, right? It's like a thermal gradient, but we can keep it separate for right now. So I'll put the whole line near the fraction there, but that's pretty much it. All right, so we'll do an example in a second. But let's look at this from a molecular standpoint. So I have a hot reservoir here, a low reservoir there, and so we put them in contact so that the jiggling molecules can collide with one another. All right, at least at that boundary, because if they're in a solid, they're not free to travel wherever they want. But it stands to reason that the molecules of the warm surface have a greater average kinetic energy than the molecules of the cool surface. So that's one definition of temperature. And through perfectly elastic collisions, the warmer molecules are going to lose, right, kinetic energy to the cooler ones, right? If a fast-moving body hits a slower one, it makes sense that the slower one is going to gain some speed, gain some momentum, and the faster one is going to lose some. Okay, so right there you can see why we have one cooling and the other warming. And consequently, the warm side cools, the cool side warms until thermal equilibrium is reached, right? So as long as molecules on the cool side are on average lower kinetic energy, they're going to gain kinetic energy on average from collisions, while the hotter ones lose it until they're at thermal equilibrium, by which there's really going to be no net flow one way or the other. Okay, so you want to be able to explain that in a simple outline. All right, so let's do a problem. There's certainly nothing obvious about this problem. Okay, what is the heat rate of heat lost? So we want H dot through window pane that is a certain area. There's a dimension. There's a certain thickness. There's L. And if the inner surfaces are at the following temperature, and we're given a K value, the conductivity of glass to be 0.84. Okay, so metals would be higher. I don't have any examples to give you in terms of contrast, but they're not radically higher. What might not be clear about this is why is the temperature 15 degrees and 14 degrees. And it looks like I'm missing a diagram that should go with this, an illustration. Let me see if I can find it. Okay, so what I decided to do is I drew in the situation. All right, and you can draw this in because, again, I'll point out what's the subtlety in this problem. So I'm talking about a 15 and 14 degree temperature difference, even though the inside is room temperature 20, and let's say the outside is freezing cold. We have the dimensions of the window, so that's not a problem. And we have the thickness, that's pretty straightforward. But the question is, why do we use the 15 and the 14 as our thermal gradient as opposed to the 20 and 0? And that's because near the window, because the window itself is in contact, that layer, if you will, between the hot and cold, that the left, the inside, is just going to be a little bit warmer than the outside, and the outside is going to be a little bit colder than the inside because there's going to be a thermal flow this way. So it's standard reason that if I have a layer of air right on each side, we're talking a microscopic layer, that's really the key one. So I'm going to draw red on the left and blue on the right to indicate those inside and outside layers that are just barely different. Okay, so it's not the major masses of air at large there. Okay, so with that in mind, then we can say H dot is going to be equal to K, 0.84 units, times the area. So the area is going to be 2 times 1.5, or 3.0 meters squared, times the temperature difference, which is 15 minus 14 in this case, all divided by the thickness. And the thickness, we're going to make sure we're in metric, 3.2 times 10 to the negative 3 meters. So we see that a really thin glass does not help our situation if we want to mitigate heat losses. All right, so we plug in the numbers, we're going to find that this is a very large number, 790 watts. So we're losing heat from that home. So you might ask yourself, well, how can we offset this? Well, if you look at really good windows, they will have much thicker, they might be double paned, okay? So they'll have a pane of glass, I'll represent with this, another pane, and between them, they'll have either a very, very thin pocket of air or even ideal a vacuum, because if there's a vacuum there, there's no way for molecules from one on each pane of window to collide with each other, so you're going to have practically no conduction. But generally there's going to be air there because of pressure issues in sealing. So air being a very poor conductor, in other words, a very small number for K, will help set that. It makes more sense to do that rather than a really thick piece of glass. The other is just not make the window so large, but generally you might want that for light purposes. Okay, the less obvious thing you can do to mitigate this is to, and that talks about wind, okay, so let me come back to that. So if we have windy out, we know that when it's windy out, things feel colder. Even though the wind is, let's say, 0 degrees Celsius, it's no colder than the air itself. So where does that chill effect come from? The wind factor, I believe it's called, wind chill. It's basically because when the wind is blowing, the outside layer is replaced by colder air. In other words, the relevant layer here, the blue one, is at 14 degrees because it's being warmed up by the heat coming out of the inside. If the wind is blowing, it keeps moving that away, replacing it with this 0 degree. So for there's going to be a greater H delta. And that's really, really important. Excuse me, my bad. There's going to be a greater temperature difference between the inside and outside, and therefore a greater rate of heat flow. So one way you can mitigate that in your house is to put curtains there. So curtains not only are ornamental, but even if they're very thin curtains, they will prevent air from moving around very easily. If they prevent air from moving around easily, then you'll get a small temperature gradient across that window, and that's really, really important. So this implies that still air is a very, very, very good insulator. In other words, a low, low value of K. So how do we, as mammals or birds alike, take advantage of this insulating properties of air? We have hair or fur or feathers for the sole purpose to trap air. And since air is a very, very good insulator, you're not going to get much heat flow through the conduction, and if it's trapped, it's not going to move. And we see from the previous problem why that's so important. Okay, so we'll finish up. Let's talk about the last one, and that is convection. Okay, and again, it looks like my diagrams did not copy over, so I'll leave it to you to look at yours. Okay, so what distinguishes convection from radiation? Radiation is just electromagnetic radiation coming off an object where there's no material between. There can be, but there doesn't have to be. Conduction is you have literal contact between your hot body and your cold body. Convection is the mass movement of molecules from one place to another. So you're literally having air mass or a water mass move, generally due to differences in density, due to differences in temperature. Okay. Okay, and so in the diagram we have here, they show some convection cells that are going anti-clockwise. Okay, like this, where we have cold water sinking and hot water rising due to density differences. And so they set up little cells that carry the water, the hot water up and the cold water down. And this is a very, very, very important driver of heat transfer in the oceans, critical, okay, and in the atmosphere. Okay, convection is a very, very important process for driving weather patterns. So if we want to take these all together and talk about how the Earth cools off, okay, you can ask yourself, can the Earth cool off through conduction? Your answer is not really, because it's not in contact with a cold body, and you won't call space a cold body. Does the Earth cool off through convection? Well, in the lower atmosphere to the upper atmosphere it can, but that atmosphere is trapped on the Earth, so it's not going to escape into space. So ultimately how the Earth cools off, as we talked about in class, is through radiation. It radiates in the infrared to outer space. Okay. Oh, last thing with convection. Remember we talked about the double pane window where we have air in here? Well, you don't want the air itself to carry heat from hot to cold. So one way to mitigate that is to keep it a really thin layer, usually less than 1 inch or so. Okay, so roughly 2 centimeters. Any gap bigger than that, then convection is going to be a major driver of heat flow, and you lose the advantage of air as an insulator. So that's something to keep in mind. All right, well, that sums up our heat modes. Make sure you understand that equation. We'll apply that with the ice cube box.